Okay, we are live. All right. How'd you guys feel about this week?
Not too bad.
Yeah, I thought that this was these were some of the easier problems that we've done, in my opinion. So, but we'll see. Okay, well, let's start going through them. We can see if we have any questions. Ashley, you were first, right?
Yeah.
Okay.
An object has a small mass. An object that has a small mass and an object that has a large mass have the same kinetic energy. Which mass has the largest momentum? Just explain that momentum is actually tied to the mass of the object, so the kinetic energy doesn't really play effect as much in momentum as compared to the mass. So a larger mass is going to have a larger momentum. The smaller mass is going to have the smaller momentum.
If they have the same velocity?
Yeah, this didn't mention velocity though, so I was confused about that.
Well, so what I was thinking was I was comparing the two equations, the kinetic energy equation, that 1/2 mass times velocity squared, and then the momentum equation, which is mass and velocity. And so I was having a hard time figuring out what I thought, because I was thinking, okay, if the mass is higher, then that's going to mean that the kinetic energy is higher. Well, I should say if they have the same kinetic energy and one has a higher mass, it means that the velocity is going to be less in the higher mass and the velocity will be more in the smaller mass to get the same kinetic energy. So then I thought, okay, if we do that into momentum, mass, a higher mass times a smaller velocity, like it's hard to tell which one would have the larger momentum. So that's where I got confused on it. But you're right, it doesn't talk about velocity. So maybe I just was thinking too much about it. Because I was like comparing the two formulas and like trying to think. I don't know. Mason, did you have a thought about this one?
No, I think she has it right. I think it's just, just basically, what one's usually going to have the bigger,
Okay.
momentum. I think it's just simply like, yeah, I don't think it needs to be too complicated.
Too complicated, because I just don't know why I guess it's fine to just say that the two aren't really related, kinetic energy and momentum. I mean, they are, but they don't depend on one another. So, okay, yeah, I'm fine with that answer. I just wanted to like clear up my confusion and make sure I wasn't overthinking it too much, and of course I was. So, okay, but that's fine. So Landon had number 2. He's not here, but I looked over his work and it matches what I did. So I can talk to you about that one if you want. Sure. So for part A, you're comparing the ship's momentum to the momentum of the shell fired. And so, oh no, that's not part A, that's part B. Okay, so the mass of the ship is what it wants to know, given the momentum and the velocity. So basically, I just rewrote the formula, obviously, which is what he did down there too. And you have to convert the velocity into meters per second because it's in kilometers per hour. So you do that conversion, and I got the 13.33 meters per second is my velocity as well. And then you take the momentum given, the 1.6 times 10 to the 9th, and divide that by the 13.33, and you get the mass to be 1.2 times 10 to the 8th kilograms. And that was my answer as well. Did you guys get the same answer?
Yeah, I got that.
Okay. And then, oh, sorry. Then for the part B, it just wants to compare the momentum of the ship, which is given, that 1.6 times 10 to the 9th, and the momentum of the shell. And so I found the momentum of the shell by multiplying it, doing the same thing that he did, multiplying the mass times the velocity. And I got 1.23 or 1.32 times 10 to the 6th. And then I divided the ship over the shell, and I got the 1,212 as well.
12.
So that's how he did those. Any questions?
No.
Okay, cool. Mason.
Alrighty. So this one was a military rifle, and it was talking about the kickback of the rifle when a bullet is shot out of it. And so I kind of took all the measurements and everything and put it down here in this, well, I made an image of it. I can't really move it, but in this the sidebar here. And then so what I did for part A, it was wondering what the recoils velocity for a 1 kilogram plug. And so I'd used this formula where the V2 final equals the M mass over the velocity of 1 over the mass. And so I plugged that in and got 12 meters a second. And then let's see, part B. Part B was asking the average force. And so what I did, or wait, what was it? It was what is the average force is extended upon the by the gun. So I did the formula the old formula from previous lessons, the V squared equals V naught squared plus the the 2A delta X. And so therefore I moved it around to get my acceleration, and I got that to be the negative 360 meters per second. And then I put that into the formula for the force and got the negative 360 newtons.
Perfect. That's what I got.
For C, I used the other formula that was given to us. Well, first, I guess they wanted to compare the forces. And so what I did is I just used the formula I gave, the newer formulas I gave us, and I put it in for the converted it around where the delta P would equal the mass times the final velocity minus the initial velocity over the time. And so when I plug that in, I get negative 1200 newtons, which is about a decrease in about 70%.
Okay. Yeah, I didn't get through that one, but that looks right from what you've done. So.
Okay. Number 4, can an object in a system have momentum while the momentum of the system is 0? I said yes, if an object of the same mass are moving in opposite directions, but the same velocity they can have a 0 velocity. Does that make sense?
Mm-hmm.
Okay.
Yeah.
Yep. Oh, I see the total momentum. Yeah.
Yeah. And then number 5 was must a total energy of a system be conserved within the momentum? I put no, because the inelastic collision energy is not conserved, but momentum is. And I got that from the simulator.
Yeah. Sorry, I was just rereading the question. It's just weirdly phrased. Must the total energy of a system be conserved whenever its momentum is conserved? Yeah, because momentum is always conserved.
Mm-hmm.
But in inelastic equation, yeah. In inelastic collisions, it's not conserved.
Things are worded really weird.
Yeah. Me too. Okay. But yeah, that sounds like the right answer to me. Okay. So I had 6 and 7. All right. So number 6, it gives the mass of the koala bear sliding on the ice at a certain speed, and it collides with another clay model bear. I'm assuming it's a bear that's initially at rest. So I made the bear at rest as the mass 2. And I put that to have a velocity of 0 so that we could use those equations from the lab. And then I did for mass 1, the mass of the moving koala bear and the speed he was going. And then to solve for the final velocity, I used that formula, the m1v1 plus m2v2 over both of the masses, the sum of the masses. And so I got that answer, and I show my work there on the Google Docs, but I got my answer to be 0.273 meters per second as the final velocity.
That's good.
Any questions about that one?
Yeah.
Okay. Then for number 7, I kind of set it up the same way. I made the one at rest, which was the goalie, as velocity 2, and his mass is 70 kilograms. And then mass 1 is the hockey puck, 0.15 kilograms, and it was moving at a velocity of 35 meters per second squared. And so it says if they have an elastic collision and the puck is reflected back in the direction in which it came from, what would the final velocities be in that case? So I used both of those formulas, the velocity 2 final formula and the final velocity 1 formula that we had in the lab. So for the first final velocity, I used mass 1 minus mass 2 over mass 1 plus mass 2 times velocity 1. And I got that one to be negative 34.9, which now that I'm looking at it with sig figs, it would just be negative 35 again. And because that's going to go in the opposite direction, so it has to be a negative velocity. And then the velocity of the hockey goalie, he's not going to move very much, just 0.15 meters per second. And I use that formula, 2 times mass 1 over the sum of the masses times velocity 1. And got that number. You guys have any questions? Okay. Okay. Number 8.
Please stick with me. This was a lot of formulas.
Yeah. I saw this one. I was like, oh my gosh.
Yeah. So this one basically is that you want to calculate the velocities of two nuclei, so the helium and the uranium, assuming the plutonium nucleus is originally at rest. So to start with, I found the kinetic energy equals the 1/2 the mass of the uranium times velocity of the uranium squared, plus 1/2 of the mass of the helium. And so I had to rearrange it so that I could eventually get VHE, or velocity of the helium, on its own, which eventually gives me the formula of velocity helium equals 2 times kinetic energy over mass of helium squared over mass of uranium plus mass of helium velocity squared to the power of the 1/2. And I put the numbers in. So velocity of helium equals 2 times 8.40 times 10 to the negative.
You don't have to read it all out. That'll save you some time if you want.
So I basically found that, and it ended up being the velocity of helium equals 1.57 times 10 to the 7 meters per second. And I used that number, and I put it in for the uranium, the velocity of the uranium, which gave me 2.68 times 10 meters per second. So there's the two velocities of the nuclei. And then for part B, how it wants me to find the kinetic energy. So I just basically took that first formula again and put it in, and I got, for the first one, the kinetic energy of the, that's the name I might want to.
Helium.
Yeah, that was 8.23 times 10 to the negative 13 joules. And then for the uranium, I got 1.41 times 10 to the negative 14 joules.
Nice.
Looks good. Looks good to me. Okay. Then number 9 was Landon's. Does somebody want to explain this one? I haven't looked at his yet, what he did.
It's a lot.
It is a lot. Okay, I'm looking at his work. Wow.
Okay, let's see. He put part A says calculate the final velocity, magnitude, and direction of the bowling pin. So it looks like what he did is did the mass and the velocity equals the mass and velocity of cosine plus mass of 2, velocity 2 final cosine theta. For the x-axis, okay, I see what he did. So he found both it looks like x, he plugs it in with the measurements that I was given. Came out with the 8.8, which I think that's what we got for that.
Yeah.
And so what he put for his final answer was the bowling pin, or the bowling ball's final velocity is negative 9.1 meters a second of its original direction.
Yeah.
Is that what you guys got?
Yeah.
Okay. And then part B what is it? Is the collision elastic, and it's not. And then C, linear kinetic energy is greater after the collision. You put after the collision, the ball will be spinning faster than it is moving. Friction, opposite of the spinning motion, which slows the spinning and produces a linear acceleration, which contributes to the increase in linear kinetic energy. I didn't get a part of that.
Yeah, I was gonna say I did not get all of that, so I cannot confirm that one.
It sounds good.
Yeah,
sounds like he knows what he's saying.
Right. He normally knows what he's talking about, right? Yeah. Some of those formulas, like, I mean, I just have to like go through and work through them myself, make sure I get the same answer. But like, I think he's using the right equations. So yeah. I can't be sure about the numbers, but I think we're safe to leave it since none of us know whether or not it's right. So I think we're okay to leave it.
I think it's good.
Yeah, it's fine with me. Okay. Well, that was fast. I feel like that was a lot easier for Landon. That was a really hard problem. And actually, number 8 was pretty tough too. But other than that, the problems were pretty straightforward. So
yeah, not too bad.
Yeah. Okay. I'm gonna go into week 8.
Just give it a formula. And then
yeah. I feel like the lab helped me understand so much more.
The lab was good this week.
Yeah. Normally the lab just confuses me, and the lab was very helpful and very like straightforward, and it taught me, I feel like, the skills I needed. So, okay. Teach one another for next week.
Hey, they're gone. My hair's gone.
Okay, there's 9 problems again. I hate that they do this. Okay. So we can find the conceptual problems and do like what we normally do with like somebody that takes 3 and 2 of them can be conceptual or something. But I don't see any. The first one's conceptual. The second one does not look very hard. The third one doesn't look very hard. The fourth one has 2 parts. 5 has 2 parts.
these are set up.
Where's 6?
8 is conceptual.
Oh, 6. And 8 is conceptual? Okay. Oh, and 9 is conceptual. Suppose you pull a nail at a constant rate. Okay. So that's a conceptual question. 6 is a conceptual question. 8.
I was like at the wrong problem, and I was like, wait, what?
So I think it'd be okay to do like 8 and 9 because one of those is conceptual and one of them's like a problem with a picture. And then 6 and 7, because it's the same thing, a conceptual and a problem. And then maybe 4 and 5. And then 1, 2, and 3, because 2 and 3 don't look very difficult and 1 is conceptual.
I can do 4 and 5.
Okay, so Ashley on to 4 and 5.
Write that down before I forget.
I know, I always write down because I always feel like I'm going to forget. Mason, do you have a preference?
I don't care.
I will do. I'll do 6 and 7. I'll have to figure this out. So you can do 1, 2, and 3, or you can do 8 and 9.
I'll do 8 and 9.
Okay, then we'll give Mason 1, 2, and 3. I'm sorry, Landon 1, 2, and 3.
Sounds good.
Okay.
That was a really fast meeting.
Yeah, it was. It was really nice. Okay.
Okay, we're done.
Awesome. Okay, well then I will see you guys next week. I was writing this down.
Sounds good. See you guys.
See you next week. Have a good one. Bye, guys.
Bye.